a number of work solutions. So Daniel's going to start with this question here, and after he's done, I will continue on with this question. So I'll just say take it away, Daniel.
Hello everybody. So we'll do 6 questions today. Josh will do 3, I'll do 3. The first question I've selected is this one. So this is a complex numbers question. Use this identity here to write sine to the power 5 theta in terms of sine thetas. So sine theta, sine 2 theta, sine 3 theta, and so on. It doesn't say in the book what or how many marks this question is. I'd say this is about a 2-mark question, so I'll just say 2 marks there. And it's a fairly straightforward question. To get sine to the power 5, I can just take this whole expression here to the power 5. And so I can say sine 5 theta is equal to this thing. So 1 on 2i to the power 5 e to the I theta. Like that. To the power 5. And I can just expand this out. So this is 1 on 32i. I'll remind you that I to the power 4 is just 1, so this becomes 32i. And over here, well, I might need some assistance to get the coefficients of this, right? And the assistance you need is in Pascal's triangle. So I'll just draw Pascal's triangle out here for you. It's a good idea to do this. It doesn't take long, and it makes sure you get all the coefficients right. So here's 1, 1, 1, 2, 1. And what I'm doing is just starting with 1s down the diagonal, and this term here, this 2, is the sum of the ones directly above it. So I get 3, which is 2 plus 1, 4, which is 1 plus 3, and the row I'm after is 1, 10, 10, 5, 1, like that. Good, so here are all the coefficients I need to create this expansion. I might shift that along a little bit. So this is 1 on 32i. So the terms are e to the I theta to the power 5 plus 5 e to the I theta 4 negative e to the negative I theta to the 1 plus 10 plus 10 e to the I theta squared e to the negative e to the negative I theta cubed plus 5 e to the I theta to the power 1 e to the negative I, that's a negative in there, to the 4 plus one more term, which I'll do over here, plus e to the negative I theta, negative e to the negative I theta to the power 5, close brackets. So it's quite a long expression in here. Your binomial expansion might be long, but it won't be complicated because Pascal's triangle tells you what you need. And I've done this in a very naive way. I haven't even attempted to expand anything. I've just written down what I've got. So I'll write it down now using de Moivre's theorem to bring these powers inside the brackets. So this is 1 on 32i, and this is e to the I5 theta using de Moivre's theorem, and I'll have a negative e to the negative I5 theta over here as well, so I might join it up with that one. So I've got, so far I've written down that one and that one. I'm just going to underline them in blue to keep track of the ones I've used so far. Let's do the one, this one here. So this is plus 5 e to the 4th theta I4 theta times negative e to the negative I theta. And over here that's, I'll do the other 5 one as well, so that's plus 5 e to the I theta times negative e to the negative I 4 theta, and the ones with the 10, so I've done that one and that one, and now I'll do the remaining 2, so that's plus 10 e to the I 3 theta e to the negative e to the negative, well that will become a positive because of the square, so I can just leave that off, I 2 theta, and that's that one, and that one, and the last one is over here, so this is plus 10 e to the I 2 theta negative e to the negative I 3 theta, close brackets. Oh, and that should be a positive. Okay, so I can push these two together because that's e to the I 4 theta times by e to the negative I theta. So this is really e to the I 3 theta. And I might write it as 1 on 16. So I'm going to bring a 1 on 2i in here. So that's e to the I 5 theta minus e to the negative I 5 theta. And I'll subtract 5 on 2i and combine these two terms. So this is a plus, no, that is a minus, minus e to the I 3 theta, and here I have minus e to the negative 3. And one more term with the 10, so that's 10 on 2i, and this is e to the I theta minus e to the negative I theta. And you can see I've written this out as sine of 5 theta, and here's sine of 3 theta, and here's sine of theta. So this whole thing becomes 1 on 16th of sine. This one here is minus 5 sine 3 theta, and this one here is 10 sine theta. So it's not terribly complicated. It might be long, but it won't be complicated for you. And the trick with getting these, all these questions like express sine 5 theta in terms of sine multiples of sine theta, is to just expand it out in this way. Josh?
Yeah. So yeah, obviously there's a lot of signs you need to keep track of when doing this sort of question. So I do support this method where you don't try and make things too simple to begin with, just write out naively what the binomial expansion is and then start simplifying things. You'll have worth noting, where was that one go on? So this one here was positive, but now it's 2 minus signs, just to make it look like that sign term that we were looking for.
Yeah, we wanted to have everything in this shape, so the 2i got brought inside, and the e to the I thetas and negative e to the I negative thetas got all just put into the right place, so they could be written like this.
And make sure you borrow that factor of 1 on 2i for the sign, just to make it work. So borrow the factor from here, inside the bracket. Okay, so I guess I'll try this question. So, well, our question is to determine with reasons, so do pay attention to the with reasons part, whether or not the line defined by this parametric vector form and this parametric vector form intersect. So with reasons means you do have to be explaining how you're getting to your result. So, firstly, how do we determine whether lines intersect? Well, I would probably start out by stating that the lines intersect when there's a solution to the following equation. So when you can have a solution to minus 1, 1, 3 vector plus lambda times 1, 2, minus 5 is equal to 0, minus 1, 5, so the vector 0, minus 1, 5, plus mu times minus 1, minus 1, 6. So the question is, can we find a solution to this? Is there a solution to this vector equation? Now, before I actually pull out the linear equations, I make less mistakes when I combine it in the vector form. So I'm actually going to write this as, so I would personally write this as lambda times 1, 2, minus 5. I'm going to leave it on that side, bring this vector over. I'll make it a minus mu, minus 1, 6. And I'm going to bring all the constant vectors onto the other side. So I think I'm just going to write down the result. So I'm going to take 0, subtract off this minus 1, get a 1, minus 1, minus a 1, so minus 2. Right, yep. And a 5 minus a 3 is a 2. So, just rewritten, we have this vector equation. So, this is a series of free linear equations, just looking at each component. So, linear equations we can solve by putting them into an augmented matrix. So, I'll just do that. I always like linking things with sentences. I think you should too. So as an augmented matrix, this is following set of equations. And I do have to be careful because I do have a minus sign here. So I have the equations 1, 1, augmented with 1, 2, 1, minus 2, minus 5, minus 6. Augmented with 2. I'll just quickly double check those signs. Yes, I think that is the right set of equations. So I'm trying to determine whether or not this system of equations has a solution. Well, we know a technique for doing that. We do row reduction, so we do Gaussian elimination. So what are our row operations? Well, I want to get rid of this 2, so I'm going to use that 1 to get rid of it. And my row operation is row 2. I'm going to make it row 2 minus twice row 1. And well, I'm going to do another row operation right after that. I'm going to get rid of this 5. So I'll write it down at the same time. Take row 3 and make it row 3 plus 5 times row 1. Okay. So let's see what happens. Well, the first equation is unchanged. This 2 minus 2, 0, that's good, that's what I was aiming for. 1 minus 2, so we have a minus 1. A minus 2 minus 2 is a minus 4. Right, minus 5 plus 5, 0, what I was trying to achieve. Minus 6 plus 5 is a minus 1. And a 2 plus 5 is a 7. So I now have this matrix, but my row reduction isn't complete yet. I need to do one more row operation. I need to take row 3 and make it equal to row 3 minus row 2, just to get rid of that 1. Alright, so the augmented matrix has been reduced to, well, I didn't change the first 2 equations. Let's see, 0 minus 0, well, that's 0, minus 1 minus minus 1, so it's 0, and 7 Okay, so 7 plus 4 is going to be 11, and that's my row reduced matrix. Now, right, so looking at this matrix, we can draw our conclusion. This matrix, well, I might just circle the leading elements so we can see them. This matrix, the last column is leading, therefore this matrix has no solution. So I would conclude, well, I'll conclude in two steps. First, this system has no solution since the augmented column is leading. Well, what does that actually mean for the original question? That means that those lines we were looking at don't intersect. So that's my final conclusion. So hence, the given lines do not intersect. Right. And I think it is important that you remember what question you were answering. I mean, I was answering that question by looking at the system of equations, but my conclusion should be about what the question was asking. So any comments?
I think that's good advice. You'll have to go back to the question. So once you've got it in row echelon form, this is a good time to look back at the question and find out what the question is asking you. If it's asking you, do the lines intersect or not, then you can stop here and draw your conclusions from this statement alone. Questions could also ask you to find the point of intersection, in which case you need to proceed further than just row echelon form and go into reduced row echelon form or use back substitution. So this is the perfect time to be looking back at the question to make sure that either you've answered it already or you need to go into reduced row echelon form to really complete your answer.
Yes, if it only asks if they intersect, you don't technically need to find where they intersect. If it asks you where they intersect, well, that's a different question.
Alright. So this is my question. I'd say it would be about a 3-mark question. Again, it doesn't specify, but I'm going to say it's probably worth 3 marks. Find the complex square roots of some complex number. Now, when you're normally dealing with roots of a complex number, you want to get it into polar form and start taking your roots using polar form. But this might be difficult to get into polar form. Fortunately, it's only asking you for the square root, so we have an alternative method for the square root. We're going to let a plus ib be the square root of this thing. So a plus ib is equal to the square root of negative 24 minus 70i. Let's suppose this is the square root, where a and b are real numbers. Then we can just square both sides and compare real and imaginary parts. So taking the square of both sides gives me a squared plus b, a squared minus b squared, plus 2abi, which is equal to a plus ib all squared, which is negative 24 minus 70i. So just using the statement above, so squaring the statement above gives me this, and expanding that gives me this. The thing I really want to do here is compare real and imaginary parts. These are two forms of the same complex number, so the real part must be the same. That means the negative 24 is equal to the a squared minus b squared, and the imaginary part must be the same. But it's important to write down what you're doing. Well, the real parts tell me that a squared minus b squared is negative 24. And comparing the imaginary parts tells me that 2a b is equal to negative 70. Notice the imaginary parts do not have an I in it. The imaginary part of a complex number is real. So I can rewrite this one slightly as b is equal to negative 35 on a. So I might label this one as equation 1, and I can label this one as equation 2, and I can sub that into there for b to find a. So gives me a squared minus negative 35 on a squared is negative 24. And I could bring everything over here so I have a quadratic equation in a squared. That's a squared squared plus 24a squared, and that's negative 35. And I'll leave it as negative 35 squared because I don't know what negative 35 squared is. And all this is supposed to be equal to 0. So to find out what a must be, I can, well, at least what a squared must be, I can solve this equation for a squared using the quadratic formula. By the quadratic formula, that tells me that a squared is equal to negative 24 plus or minus the square root of 24 squared minus 4 times 35 squared, negative 35 squared, so that becomes positive, all over 2. Which is a bit of this is going to cause me some trouble here. That's going to become negative 12 plus or minus the square root of 12 squared plus 35 squared. Remember, there are no calculators in your test, so you need some method for determining what this number is. I might leave that, and what can I do?
Move to Josh's.
Move to Josh's board. Josh, I'm going to steal this side of your board. I'll leave that up and just steal what you've got.
Yeah, I just need to write down 3 more vectors.
Alright, can I just steal it now and you can have it back later?
Yeah, sure.
So I need some method of finding out what this is. I think it's going to be a perfect square. So let's see what happens. So and it's going to be something a little bit bigger than 35. So maybe I'll say 12 squared plus 35 squared. I think it's going to be equal to 35 plus a little bit. U squared. U greater than or equal to 0. That's my suspicion. Because I'm in a test, I think this is going to work out okay, but I don't know what it is yet. And so I can expand this, I get 144. I know how to square 12, that one's okay. 35 squared is this thing, which is 35 squared plus 2u times 35 plus u squared. And I can cancel off the 35s, like that. And I get 144 is equal to 70u plus u squared. So I can try a few values. If I let u equal to 1, I get 70 plus 1, which is 71. No. If I let u equal 2, then I get 140 plus 4, which is 144, so u equals 2. And that kind of numerical witchcraft is what, and you need to use something to be able to deduce what this square is. So I've used some kind of reasoning here to find out what this square is. It's actually just 37 squared. So a squared is negative 12 plus or minus the square root of 37 squared, which is negative 12 plus or minus 37. Which means a squared is equal to, let's see, that's either going to be 25 or negative 49. So a squared must be 25 or negative 49. And it's at this point you use the fact that the real part of an imaginary number is real. So it can't be the negative one. Hence a squared can only be positive 25. Well, since a is real, a squared is equal to 25, so a is equal to plus or minus 5. A is only plus or minus 5. And then you can substitute that back into equation 2. So when a is positive 5, then b must be equal to negative 7. When a is negative 5, b is equal to positive 7. So the roots are 5 minus 7i and negative 5 plus 7i. So that's the question. It's probably a 3-mark question because there's some work to be done here in actually taking this square root. Otherwise I'd say it would be a 2-mark question. Josh?
So yeah, I guess this last part, it's really common for students to get to this information that a squared is 25 or minus 49, and yes, you must remember that a isn't a complex number. Well, it's a real number. In this case, it's actually an integer. So it doesn't have any imaginary parts, so that you can rule out one of those 2 cases. Right.
Good.
Yeah.
Alright, I'll clean that up. Oh, you found it. Good. Sorry, it gets a bit dirty. Sorry, Josh. There we go. Nice and clean.
Thanks. I'm sure I put these vectors. I need
a bit more of this.
Yeah, there you go. Try this. Right, so this is the next question I'll be answering. So it's taken from test 2 version 1A 2014. This is question 2. It doesn't give me how many marks this is worth, but I think this would be around about, it could be around about 3 marks. Right. So what we want to do is, we want to determine what conditions you'd have on this general vector B, such that it belongs to the span of these 3 vectors. This is a question set in R4. So you have 4-dimensional vectors. Okay. So, yeah. So, well, the condition you're going to have a solution to the equation where you take a combination of these 3 vectors, so say lambda 1 this vector, plus lambda 2 this vector, plus lambda 3 that vector is equal to this. But I'm going to jump straight to the system of linear equations we're going to need to solve. So I would probably start by writing out that we can answer this by considering the augmented matrix and here's my augmented matrix. So it's going to be, the first column is going to be that first vector, 1, minus 2, minus 2, 6. Then the second vector for the second column. And the third vector for the third column. Augmented with, and I'm going to do something which some people might think is unusual. I'm going to write down that general vector, but I like to give myself a bit of space just to make sure when I'm doing my row reduction I don't, well, it makes my calculations easier. So this is actually just a vector. I've just given myself a bit of space. So when I do the row reduction, I'm going to make less mistakes in my row reduction. Now I don't have much space down here, so I'm going to continue up here. Now if you did have something like this, you're starting on a new page, I suggest you actually write out the row operations. Don't use the arrow notation. So applying the row operations. So what are my row operations? Well, I want to get rid of this 2. So I'm going to take row 2, make it equal to row 2 plus twice row 1. So I'm going to use this nicely provided 1. I will also do the row operation row 3 is row 3 plus twice row 1. So again, using that 1. And row 4 is row 4. And I need to take away 6 times row 1. So applying these row operations, we get, so what do we have? Here's my augmented matrix. I have the 1, 3, minus 3, B1. Alright, so minus 2 plus 2, and it's 0. That was the whole point. I have a minus 5. That's going to become a plus 6. So minus 5 plus 6 is 1. A 4. This become a minus 6. 4 minus 6 is minus 2. And here I'm taking B2 and I'm adding on twice B1. So I would write that as 2B1 plus B2. Just I find it easier to read that way. Next, so almost the same sort of operate. Well, it's the same, pretty much the same operation. Minus 2 plus 2, 0. Minus 4 plus 6 is 2. 2 minus 6 is minus 4. And this one will become twice B1 plus B3. And the last one, alright, we have 6 minus 6, 0. I've got to be careful here. This is going to be 3 minus 18. So 3 minus 18 is minus 15. This will become a 12 plus 18. So there are 2 minus signs here. There's a minus 6 minus 3. So 12 plus 18 is 30. And this becomes minus 6 times B1 plus B4. Thankfully, actually, there's only 2 more row operations I need to do. So my next set of row operations, I would like to get rid of this 2. I'm going to use that 1. So I'm going to take row 3, make it equal to row 3 minus twice row 2. And after I do that, I'm going to get rid of this 15 using the same one. Make row 4 equal to row 4 plus 15. Oops. Plus 15 row 2. Okay, so my first two rows haven't changed. I'll just copy those out correctly. And let's do our row reduction. Right, so these zeros don't change. I get a 2 minus a 2, that is a 0. I get a minus 4 plus a 4, that's another 0. And here's where this notation I think comes in handy, is I'm going to have a 2b1 minus 4b1 will give me a minus 2b1. I'll take away 2 of these to get a minus 2b2, and the b3 wasn't modified. Okay, next one, minus 15 plus 15 is a 0. A 30, this becomes minus 30, it's another 0. And, okay, so this is going to become, so 15 times that is 30, 30 minus 6 is 24, so I get 24 b1. Let's see, there's a b2 involved, it gets a 15 b2. There's no b3 term, and I just have my b4 from before. Right. Okay, so you can see that there's not really any more work I can do without knowing the b values. So, well, we can see that looking at this form, this will only have a solution when this last column is non-leading, which means I need these two terms to both be 0. So, looking at this form, I can say that there is a solution, and I might actually at this point remind us what the question was, i.e. the vector is in the span given, or the span of the vectors given, to be more precise, precisely when these two terms are 0. So when minus 2b1, mistake, minus 2b2 plus b3 is 0, and when 24b1 plus 15b2 plus b4 equals 0. Alright, so this does characterize precisely when this vector is in that span. So if these are non-zero, you don't have it in the span. When these are 0, you do have it in the span. So, any comments?
Looks good. Looks really good. I like this method of writing your B's out in a really kind of in this structure. So it's just a vector, but it's got a lot of white space in it, so you can fill it out and do all your arithmetic in the way that you're used to with elementary row operations.
Yes.
So I like it.
You don't need the space. You can do this if you just remember the B1s only combine B1s and do it like that.
Yeah, and
the white space is nice.
I think there's a lot of merit in this. How many questions how many marks do you think that's worth, Josh?
Tough to say. I thought I saw it worth 4 marks in one of the versions.
Yeah.
So it could be worth up to 4 marks depending on how the marking scheme is split up.
Something you might have noticed with all these questions is they're quite long. So all the questions, a few of the questions you've seen in this stream have taken many boards worth of work. So be prepared for long questions when you get into your exam. You do get an extra 5 minutes, so the exam is actually 25 minutes long as opposed to the regular 20. So you will have a bit of extra time because the questions are quite long. So hopefully you've all seen questions like this before. There is an algorithm to follow. The polynomials will be different, the powers will be different, that number there will be different, but the algorithm is always the same. So once you know what the algorithm is, you'll be able to do all these questions. The first thing you do is convert everything into polar form. Z actually it's going to be negative 64. So maybe before we even do that, so z to the 6 is equal to negative 64. There we go. That's a more familiar form for this kind of question. This kind of roots of unity question. Now we'll let everything be in polar form. Let z be equal to r e to the I theta, and negative 64 is equal to 2 to the 6 e to the negative, positive, pi I 1 plus 2k, where k is an element of the integers. Notice I'm using a non-principal argument here for the negative 64. So I've got all possible representations of negative 64 in polar form. And this is what's going to give me my multiple roots, because we know this is going to have 6 complex roots. And I need to get that multiplicity out somewhere, and it's here, which is where it comes from. So I'm letting my two things be polar form. Z to the 6 is supposed to be equal to negative 64, so I'll just write it out. Z to the 6, so that's r e to the I theta to the power 6 is equal to negative 60. Well, that's z to the 6, which is negative 64, which is 2 to the 6 e to the pi I 1 plus 2k. And this I might write out as, well, I'll leave it like that. What I'll do now is compare the modulus and argument of these two numbers. Well, I do want this as r to the 6 e to the 6 theta I. What I'm going to do now is compare the modulus and argument of the two numbers. So the modulus is easy, that's r to the 6 is 2 to the 6. And the argument is 6 theta, not 6 theta I, the argument is 6 theta, which is supposed to be the argument over here, which is pi pi times 1 plus 2k. Good, so I can now solve these two things, and k is just an integer. So now I can solve these things. I can get r must be equal to 2. I get one value for r, and I get theta is equal to pi on 6 times 1 plus 2k, where k is equal to an integer. This gives me lots of different values of theta, and I'm going to write down a few of them. So some examples might be, I'm going to get a few of them, so I'll do it over here. Pi on 6 when k is equal to 0. I'll also get 3 pi on 6 when k is equal to 1. 5 pi on 6. 7 pi on 6. And a few others, lots of others. I'll also get some negative values of k, so I get negative pi on 6, negative 3 pi on 6, negative 5 pi on 6, negative 7 pi on 6, and perhaps others still. Lots and lots of possible values of theta here. The good news is I'm just going to cherry pick out the principal values of theta. So the ones which are between negative pi and pi. So that's smaller than negative pi, so I'll get rid of that. I'll get rid of everything less than it. I'll keep this. This is squeezed in with between the principal ranges. I'm going to keep all this stuff, and I'm going to get rid of that because it's bigger than pi and all the others as well. So I've just cherry picked out my principal arguments here. This gives me the desired roots. Hence, z is equal to 2e to the, well, it could be plus or minus 6 pi. So, pi on 6 I to e to the plus or minus 3 pi on 6. So I'll write that as pi on 2 I, and to e to the plus or minus 5 pi on 6 I. Notice that when I perform this operation of crossing them off, I'm not actually removing any solutions, I'm just getting rid of the non-principal ones. These extra arguments up here just give me repeated roots. So this 7 pi on 6 is actually just going to give me the same complex number as this negative 5 pi on 6 over here, but I don't need it. So I'm just getting rid of the non-principal ones and having only the principal arguments. Okay, I've got my complex roots. Once you have your complex, so that's part 1 done. Once you have your complex roots, you can factorize your polynomial into linear complex factors. That's always the first step. The question doesn't actually ask me to factorize this into complex linear terms, but I'm going to do it anyway, because that's the first step in getting it into real linear and quadratic terms. So this is part I now. So z to the 6 plus 64 can be written out as z minus 2e to the pi on 6i times by z minus 2e to the pi on 2i z minus 2e to the negative 5 pi on 6i z minus 2e to the negative 5 pi on 6i. So we know that if you have a root of this equation, then we have this. Well, if these are the roots, then this is the factorization and complex linear factors. And I've written them up so that the roots occur in complex conjugate pairs. The reason I'm doing that is so I can now condense these into real quadratic factors. Because when you have a factorization like this, you can combine it, and as so. Well, I'll show you how to combine it. So this is z squared. This becomes minus 2 e to the pi on 6I. So maybe I'll write this as minus 2 pi to the 6I plus 2e to the negative pi on 6I z plus that times that, which is just 4. I'll write it out one more time. So that's 4 times e to the pi on 6I minus pi on 6I, like that. So that's the first term here. Now you might start recognizing some of this stuff. This is going to be just 4 because the two arguments here will cancel with each other. And this is almost cos theta. So I'll write out the next one as z squared minus, let's see, this is going to be, well actually maybe I'll just write out the whole thing, because I've just seen, I'm supposing I've just seen the pattern, I might put a cross through that, save myself some space. I can write this as z squared. This is going to be, I need to divide this by 2, so this is going to be negative 4 times e to the pi on 6I plus e to the negative pi on 6I over 2 plus 4, like that. So that's just rewriting that term there, times by z squared. I'm going to do the same thing for these two. That's 4 e to the pi on 2I plus e to the negative pi on 2I divided by 2. There's a z there, z plus 4, and z squared minus 4 e to the 5 pi on 6I plus e to the negative 5 pi on 6I divided by 2z plus 4. Good. So this thing here is cos of pi on 6, which is root 3 on 2. So I can rewrite this whole thing as z squared minus 2 root 3 on 2. So it's 2 root 3 z plus 4. That's my first term. Cos of pi on 2, that's just 0. So my second term is even better. That's z squared plus no z term plus 4. And my final term is z squared minus, so 4 times cos of 5 pi on 6, and cos of 5 pi on 6 is negative root 3 on 2. So that becomes negative 2 root 3 z plus 1. Again, a very long question. It's a long exam. There's probably only going to be 3 or 4 questions in it, but there is no time to make mistakes. You need to know exactly what to do when you're faced with a question like this in order to have any hope of actually completing 3 such questions in 25 minutes. So don't be lulled into a false sense of security thinking, only 3 questions, 25 minutes, no problem, easy. No, the questions might be easy, but they will be long. And you need to be able to perform a whole question like this with no mistakes in order to be able to really do these questions properly and do well in the exam.
So yeah, I think this question it's very important you do start from the complex linear. If you try to jump straight to the real quadratic and real linear factors, you're probably going to have a hard time doing that. Yeah, it was nice to see all those roots written out. Unfortunately, I erased them. But nice to see all the possible roots written out and picking out the ones that actually are the ones we want.
The principal ones.
The principal ones. Yeah. So I'm going to answer, what might be a similar question. Again, it's about complex numbers. And again, we're going to have to do something with the principal argument. So we have this complex number, minus root 3 plus 3i. The first task is to find a polar form for this number. And once you have that, you can find the principal argument and the Cartesian form, the a plus ib form, of z to the power of 19. Thanks. Alright, so actually the first thing I want to do with this question is actually just draw a quick picture to make sure I know where this complex number is, so I'm not going to make any mistakes. getting into polar form, you really need to know where in the complex plane it is. So my quick picture, we have the real axis and the imaginary axis, and this is minus root 3. It's somewhere between 1 and 2, and also 3 here. I think some people like 3i, and our number here is z. Okay, so actually what I would like to do, because I find this the easiest way to do it, is I'm going to work out this angle here, call it alpha, and I'm going to realize that this number, this angle I actually want, the argument I need for this polar form is going to be pi minus alpha. So, alright, so how do we find the argument here? Well, again, I'm going to need just a quick little picture. This is a triangle. Yeah, so this is a triangle. Maybe I shouldn't do that first. I should do something else first. So note that the argument, this is actually the principal value argument of z, is going to be pi minus, and it's going to be minus the tan. So where I've written it here, this has length, so it's opposite over adjacent, so it has length 3, and I'm dividing that by root 3. So just using the length of this divided, length of this divided by length of this, which is pi minus the tan of root 3. Alright, so now that I have that, just remind myself of the little triangle, the 1 to root 3 triangle, which has angle pi over 3, 60 degrees in one corner, and pi over 6 in the other. This is going to be pi over 3. So it is pi minus pi over 3 is 2 pi over 3. Okay, so that is actually the principal value argument for this one. And I also need to know the modulus. I need to know how long this complex number, how far from the origin it is. So we have that, and the modulus of z is modulus of minus root 3 plus 3i is the square root of minus root 3 squared plus 3 squared, which is root 3 plus 9, or in other words, root 12. Well, 12 is 4 times 3, so I actually can write that as 2 root 3. That just makes it look a bit nicer. Okay, so I can answer the first part of the question. First part, find the polar form for z. So, well, z is going to be 2 root 3 e to the I 2 pi over 3. So that's the first part of the question. Next part, I need to look at z to the 19 and get some information about that. Alright. This is linking words, so continuing. We get z to the 19. Well, I already know what z is in polar form. It's 2 root 3 e to the I 2 pi over 3 to the power of 19. Well, this just becomes 2 root 3 to the 19 e to the I 2 root 3 2 pi over 3 times 19. So just multiplying those two powers together. And, well, I'm going to have to rewrite this argument. And I think the easiest thing to do at this point is, let's try and find the closest multiple of 3 we can to to 19 and just split it up. So I'll write it here. This is 2 root 3 to the 19, e to the I, 2 pi over 3, and 19, well, closest multiple of 3 is 18, so I would write it as 18 plus 1, just because now when I do this, I have 2 root 3 to the 19, e to the I. I'll do it slowly because I'm prone to make mistakes. 18 divided by 3 is 6, and 6 times 2 is 12, so I'm going to get I of 12 pi plus 2 pi over 3. Well, this is a multiple of 2 pi. It's actually 6 times 2 pi. So, in terms of an angle, this is just the same as 2 pi over 3. So, maybe one more line. Right, 2 root 3. 19. Oops. Yes, 19. E, this is going to be the same as e to the I, 2 pi over 3. So I might, just at this point, remark what I can see straight away looking at this what the principal value argument is. It's actually just this number here. This is between pi and minus pi. In fact, it's at the exact same angle that the original number was. That's quite nice. So, right. So I might just actually state that before I move on. So you can see that the principal value argument, so it's capital A, of z to the 19 is actually just 2 pi over 3. Alright, now I need to get, that's one part of the question. Final part, I need the Cartesian, the a plus ib form. And, well, I'm going to use Euler's identity. So, how to rewrite a complex exponential in terms of cosines and sines. So we have that, maybe a comma. And what do we also have? Just z to the 19 is going to be equal to, well, 2 root 3 to the 19, the cosine of 2 pi over 3 plus I sine 2 pi over 3. I can do better than this. This is in some ways Cartesian form, but these two I do know I can do this. So 2 root 3 to the 19. So cosine of 2 pi over 3. I can actually get it from this, because this is right angle, wrong modulus. But it is going to be, let's see, well, maybe I should actually just do it from this triangle. So this does have, I can get it from this. So it's going to be minus 1 over 2. So, yeah, minus 1 over 2. Plus I, and the sine is going to be root 3 over 2. And personally I think that's good enough. You may wish to see the a and the b explicitly, in which case you may just wish to expand it. Although I forgot to write up one part of the question, which is powers of real numbers can be left unsimplified, so we don't mind if we see these high powers of real numbers. That's not really what we're not testing your ability to simplify that. Alright, so I might stop there. So what do you think, Daniel?
I think there's a lot of good things here. First of all, this one here may not be considered Cartesian form. There's some places would consider this to be polar form, so it's really important to actually go a little bit further. The thing I really like is that Josh did these two diagrams here. They perform very important roles, and you actually got a lot of mileage out of them. First of all, to convert your complex number into polar form, this was important because we made sure that the argument was correct, and we were able to figure out the tan of some things based on this triangle. So that was important when we were actually constructing the polar form. But it got used again down here when we were actually converting from polar form of Z19 back into Cartesian form. So these were very useful. This diagram here, we knew where 2 pi on 3 was, so we made sure we got the right sign in front of the cos, and then this triangle down here gave us the correct values. So a diagram like this is really important to get the plus or minuses right in your Cartesian form, and a diagram like this is really important to get the actual numbers right. So I was really pleased that these appeared, and they're very useful to you whenever you're doing questions about polar form of complex numbers.
So that was 6 questions, I think.
Yeah, we're all done.
Yeah.
Cool. So good luck in your class tests. We'll do one more live stream sometime before the final exam. So good luck.
Yeah, good luck.